Need to connect. Okay, this is superfluous to record this part, but whatever. So today I thought that I'm going to talk about partially of a paper of Dan Russo that came out last year. This paper partly talks about, I just want to present. Oh. Right. There. Okay, I solved that mystery. Turn off the... No, that's not that. Oh, yeah, okay. Haha. So before we jump on the new topic, which is going to be an old topic, let's just clarify something about this L-user dimension confusion that ensued at the end, because I made a mistake. And the mistake was that somehow when I was doing derivations, I didn't notice that some inequality was going the wrong way. And you remember that we tried to bound the L-user dimension for this linear setting, and I started to sum up the errors and the squared errors because it was really useful for the linear analysis to get in some determinants and whatnot. And there the inequalities were not going the correct way. And then I claimed that, okay, you can fix that by increasing the accuracy with which you are measuring these discriminant functions. And then here is one page that explains how you can do this. So just very quickly for this page, so this is for the last lecture. So you have this discriminant function, which for our case was mapping. It was just linear, right? Like these were vectors, and then you just take in their products. These are vector spaces you take in their products, and that's your discriminant function. And then we said that an L-user sequence is a sequence of points in these data points. And an L-user sequence, like I define now L infinity and L2 L-user sequences, and then they have two parameters for the sake of generality, epsilon1 and epsilon2, and then there is this L infinity parameter. And so we can say that, so there's a definition, x1 to xn is an epsilon1, epsilon2 L infinity L-user sequence. If for all indices between 1 and n, there exists a parameter vector theta in such a way that we are surprised to see the ith data point, so the discriminant there takes a big value, whereas for all the previous data points, the discriminant took a small value, okay? So there is still a surprising observation to be made. Then that's like, if you can do that for n steps, then you have an n length n L-user sequence. And you can collect all the L-user sequences into a set. So this is this set. It's parameterized by epsilon1 and epsilon2. Which is the definition. And you can do the same, but now instead of taking the maximum of the errors, you take the sum of the errors, the sum of the errors squared, okay? And because you are squaring here, you're also squaring this error there, so that they are homogeneous. And the definition is otherwise the same, and you can collect, oops, the set of these. How do you undo? Okay. I inadvertently pressed erase. Okay. And then you can notice that these sets are decreasing in epsilon1. So if I increase epsilon1, then the set shrinks. And if I increase epsilon2, then the sets are increasing. Okay. And then it follows that if you take L infinity L Euler sequences that are of length n, then just because you can simply square these and sum them up and satisfy this inequality, it holds that if you have an L Euler sequence of length n for L infinity, the L infinity definition, then you will have an L Euler sequence for the L2 definition, but you have to scale up the epsilon2 by a factor of square root n minus 1, because here you are summing at most n minus 1 terms. The largest value that I can take is n minus 1. Okay, so that's just a simple observation. And then it follows that the maximum lengths for L Euler sequences of the L infinity type with a parameter epsilon, where the second parameter is scaled down by a factor of square root of d, where square root of d is the maximum length of L2 L Euler sequences, is upper bounded by this d parameter. Okay. So again, if you define d as the L Euler, the maximum length of L2 L Euler sequences at the scale of epsilon, then the claim says that the maximum length for the L infinity L Euler sequences where the second parameter is scaled down by a factor of square root d is also bounded by the same number d. Okay, so it's sufficient then to upper bound this if you can afford to increase the accuracy there by a square root of the factor, which in the algorithm you can do. And so for seeing whether this is true or not, notice that if for some n this set is empty, if for some n this set is empty, then of course it's also empty for n plus 1, because this was like an increasing definition. And so it suffices to show that for this claim to hold, it suffices to show that there is no L Euler sequence of the L infinity type with the required parameters of length d plus 1. Okay? And for this, what you can do is that, well, you can notice based on our previous containment here, that the L infinity sequences are where the second parameter is scaled down by a square root of d factor of length d plus 1. They're all a subset of this, where n right now is d plus 1, so n minus 1 is d. So multiply with a square root of d, you get an epsilon there. Okay. So this containment holds, and of course you can intersect this with the same set of sequences, and by the definition of d, this is empty. So it follows that, of course, then this is also empty, and it follows that the claim holds. All right. Anyways, once the lecture notes is going to be up, this is going to be clarified there. Is this clear?
For claim 2, what's going on after the arrow?
Oh, this is just explaining what I explained in words, like this, saying that if you have these witnesses for the L infinity error, then the claim is that there are going to be witnesses for the L2 error as well. That's how you prove the claim.
Oh, I meant like I can't read it.
Yeah, it just says that if θ1, θm-1 are witnessing that this x1, xn, a specific x1, xn sequence is an alluder sequence. So here this theta's, right? Like for every I, there is a theta. You can call it theta I, and then you would have a witness sequence of thetas. Okay, so now we say that, okay, fix any x1, xn, pick the witness sequence, which is witnessing that this is an L infinity alluder sequence with these parameters. Then we're going to claim that this is a witness sequence for the L2 setting as well. Therefore, this is also, this sequence is also an L2 alluder sequence.
And that's an I-1 in front of the epsilon squared. Sorry, like I can't.
That's an I-1. Yeah, that's right.
Okay,
and this is an N-1, which is because I is smaller than or equal to N.
Okay.
That's it. All right. So let's find good notes. All right. So the paper I want to talk about partially is approximation benefits of policy gradient methods with aggregated states. And I'm saying that I'm just going to partially touch this paper. Oh, this is this year, actually. It's 2021. Quite new. So in this paper, Dan is arguing that policy gradient methods, which we haven't talked about yet, do have some benefits in terms of approximation error. So what is this thing? So if you recall, the approximate policy, okay. No. Okay. All right. There. So approximate policy iteration. Everyone's favorite. So this is the result that, no. This is the result that we got at the end. So we were talking about this algorithm that assumes that the action value functions of all the policies can be accurately represented up to an epsilon error in L infinity norm. And then there is a natural way of extending policy iteration to this setting where you introduce the function approximator to deal with the fact that you have too many states, and you just need to extrapolate to states that you don't have a chance of like visiting or learning about. So this is in the context of planning. So there is this algorithm that you can run, which mimics policy iteration, except that in every step when it comes to evaluating a policy, it uses an optimal design, which is a function of the feature map, to come up with state action pairs from where it runs a bunch of rollouts with the current policy of a certain length that you can adjust. That was age, and collects returns along these trajectories, takes averages, solves the resulting weighted least squares problem. Weights are coming from, again, G-optimal design. And this way, it creates an approximation to the action value function of the policy. And then it takes the next policy, which is greedy with respect to this. This is polynomial in all the quantities of interest. But what happens at the end is that the approximation error gets inflated. I don't know whether I can point here. No? Okay. So I wish I knew how to use these modern tools, but okay, so you see the first displayed equation. Data is more than equal to 4 times 1 plus square root d. D was the dimension over 1 over 1 minus gamma cube times epsilon. Epsilon was the approximation error. And then there are the other terms that are totally under your control. K is the number of iterations. So the second term gets small if K is big. The third term, there is a capital H in that. It gets small as H gets large. The last term, it gets small as M gets large. That's the number of rollouts from a given design point. And so you can control everything except in the first term, we blew up the approximation error by a bunch of factors. We blew it up with square root of d. And then we had some arguments, and then that's already typed up, that says that, well, the square root of d, in a worst case sense, must be there. Like, bad news, you can't do much with that if you insist on algorithms that use polynomially many queries in the relevant quantities. But how about this other term, this 1 over 1 minus gamma cube term? Like, we didn't have any argument that would have said that that should be there. Now, notice that our errors and all the value functions kind of naturally scale with 1 over 1 minus gamma. So that's kind of the scale, the maximum scale. So one of the 1 over 1 minus gammas can be justified here by just saying that, well, okay, that's like, should be there because that's the scale of the functions. So if you want to talk about relative errors, then like you could normalize things, and then one of the 1 over 1 minus gammas would go away. But we still have 1 over 1 minus gamma squared. And do we really need that 1 over 1 minus gamma squared to be there? So that's where Dan's paper comes in. It's a lower bound. It starts with a lower bound for, how do I? All right. So the paper doesn't start with the lower bound, but like one chapter in it or one section in it is a lower bound. So there is a lower bound for API. It's not quite the API that, not quite the approximate policy iteration algorithm we're talking about, but it's very close, and maybe it's going to be a homework to verify that. The lower, like the algorithm that we discussed in class is also subject to this lower bound. The only difference between the algorithm that Dan is talking about and the algorithm we're talking about is that in the algorithm we talk about we run optimal design and do this truncation, whatnot, and he just doesn't do that. But in his example, based on what I see, I don't think optimal design would do much. So I think that in his example, the same problem would happen. So what does this result say? So what does Dan's result say? So this is his theorem. Says the following: for every gamma, because we care about the scaling with the horizon. And I guess every epsilon as well, because we care about the approximation error. So this is the approximation error. There exists an MDP. It's not even a big MDP. Well, it's an MDP. It's a finite MDP, such that there is a policy such that if we initialize API with this policy, then API generates these policies. Okay, pi1 is the very first one, and so on and so forth. Such that, well, he writes it in a fancy way, but what happens is that you can have a very bad initialization. You initialize the policy like in some way, API, and then in this example, API is going to alternate between the first two policies. So it's like after it switches to a policy, it switches back to the first policy. So we can strengthen his result by saying that the best performance that you will ever see from API in this MDP is going to be okay. So there exists some initial state distribution, and recall that when I write instead of a state distribution, that just means that okay, that's the value when you start from that distribution. So it's the expected value. It's the notation that I used before. And this is lower bounded by some constant. I think it's like 2 or something, times the approximation error times 1 minus gamma squared. So the 1 over 1 minus gamma squared needs to be there. So API doesn't escape this. And so here, the only thing that I didn't specify is how the policy evaluation done. So in policy evaluation, we are feeding the policy the action value map in step T is going to be minimizing the weighted, I don't know, with some weighting, a weighted 2 norm squared. Error, and then you use the actual action value function as the target, so it's idealized in the proof. So Q is in the span of the features, so I just usually denote it by f of phi. And the weighting here used is going to be uniform. Now, okay, you might suspect that the uniform weighting may be a very bad choice. But looking at the proof, it happens that it's probably not a bad choice. So what is this MDP? And how do the features, okay, so here there is an MDP and there is also a feature map, right? Corresponding to that MDP that we're talking about, because this approximation error is defined as the worst case error of approximating the action value functions. And here, in his paper, you will see a different definition for the approximation error, but you can account for the differences. So he's talking about state aggregation. So state aggregation is the idea that you just like lump together some states. So if you have the state space, this is your state space, it's nice square. You would just like lump together some of the states and create this abstract states. Like this is going to be just one abstract state. I don't know how you think about this group of states as one. And that's the idea. And with function approximation, since these are treated as one, that means that the action values for every state that belong to the same cluster or group have to be the same for these approximate value function representation. That's the compression that we're applying, right? So the way we are compressing the state space is that rather than like looking at the minuscule details of the states, look at the group identity, and we just treat states as identical if they belong to the group. And you can do that with feature maps as well, right? So so what is the feature map corresponding to something like this? Well, the feature map would have this pattern that, but in this case, the number of dimensions is going to be 6, one dimension corresponding to each of the clusters. And then if you have the states and the actions that belong to the first cluster, they would be here in the top. Well, the ordering doesn't really matter, but it will be much easier for me to show you how the feature map looks like if I can reorder the states and actions in a convenient fashion. So this is group C1, this is group C2, this is group C3. So this is going to be C1 cross A. So all the state action pairs that belong to C1 cross A are on the top in my ordering. And I just put a bunch of ones here. in the first column, and then zeros everywhere else. And then do that for C2 as well. But apologies for the crowded figure. And then do it for C6. So this is C4, C5, C6. And this column of ones travels. So it's basically an identity matrix where you would duplicate every row as many times as needed. And so you do this. And these are the features. So under these features, if you multiply it out, the functions that you can get are constant over every group, right? Because they share the same feature vector, the state action pairs belonging to, oh, okay. Okay, yeah, okay. So this is for state features. For state action features, thanks for asking. No one asked. Guys, you should pay attention. This is not right. This is for states, state value functions. So state value functions, this is correct. So, but I have to cross. I have to cross the action components. Okay, I was just thinking about states. Like if state functions of state, the features that you get are like this. If you want to get the same thing for state action pairs, then you have to create a copies of this, and the dimension is going to be also multiplied by a. And so this little one, like that one, is going to be expanded to a little identity matrix, okay, where there are a columns here and a rows. So every one here is expanded to that little identity matrix. With that, you can distinguish between the different actions, but you cannot distinguish between the states that belong to the same group. So then this would correspond to, you know, some state and action one, and then this is some state and I don't know, action, the last action. And then you start again, the same state, a different state, the same group, action one. So now, since these states belong to the same group, they have the one at identical position in their feature vector. Therefore, they are not distinguished, but the different actions per state are distinguished. It's like a tensor product construction. Anyways, if you do this, then you can represent all the action value functions that are constant across all partitions and actions. It's basically, you should imagine that like there is this action dimension, and so you can list a different functions. Right.
Shabat, a quick question. So in this example, the vectors corresponding to the different groups are all orthogonal. But in general, for state aggregation, do they have to be orthogonal, or is it still considered state aggregation if you're not?
That's not considered state aggregation. In state aggregation, this is the pattern. So this is yeah, like there is people call it soft state aggregation when that's not happening, but that becomes a really soft area as well. I don't really know what the definition there is. The intuitive idea in soft state aggregation that if you look at the individual basis functions here, they look like as, like membership functions of which state belongs to the group. There you have a 1, and you have these indicators, right? So the basis functions are indicators, and they don't have an overlap. So this is basis function 1. Okay, maybe use a different color. And this is basis function 2. And they're not overlapping. And in soft state aggregation that people also talk about, you would allow such overlap. So do things like that. And in early neural network literature, I don't know, radial basis function networks, when this is a continuous space, were considered to be, I don't know, interesting subject. I mean, in approximation theory, people study these and their properties. And I guess it helps with smoothness if you don't have these sharp boundaries that you have with the indicators. If you want to represent some smooth functions, you will have a hard time doing that with piecewise constant functions. If your basis functions are smoother, then you will have an easier job of representing smooth functions. So if you have some prior reason to believe that your wave functions are smooth, you're better off with soft state aggregation than with hard state aggregation. But there are then many variations, like why would you stick to these non-negative basis function types? And then the radii was referring to that, like with a distance from a center point, things are decreasing uniformly, or like changing uniformly, not necessarily decreasing, and so on and so forth. It's a big topic. But here, so then was just going after this very simple thing of like, let's just aggregate the states and let's see what we can have. So back to our theorem. So his whole paper is about state aggregation. So this feature map is about state aggregation. And in the example that he has some MDP. And very abstractly in the MDP, he has like basically groups of like pairs of states are grouped together in the MDP. And the MDP sort of has some chain structure, and you can stay, and like it has some extra structure. And what approximate policy iteration you can force it to do is that it's going to the MDP is constructed such that you want to go towards left. You could go towards left at 0 cost. That's what the optimal policy does. And you initialize approximate like the policy in approximate policy iteration in such a way that for every second one, it moves. So that's good. But for these guys, it stays. And if you do that, then for the next iteration, what happens is that it switches to this other policy, which is going to stay here and going to move here and then stay, and then here stay. So and then it alternates between the two. So it goes back and forth between these two policies. And both of these policies are pretty bad. You can make it, well, this bad. And the approximation error is going to be small because the states, basically these are pairs of states. So the states in the upper and the lower kind of behave identically with some small differences in terms of the rewards in the dynamics. It's a very cleverly constructed example based on an example that I think goes back to Dimitri Bertzikas and John Titiklis, his neurodynamic book that we talked about. So that book, the examples in that, they are fantastic. So they write about this chattering phenomenon for approximate policy iteration. Basically, this is it. And the weighting that we started to talk about is uniform across all these states. But since these are, so the way this aggregation is done, I don't think an optimal design, like you need one component here for each of them, because these are the different dimensions, so to say. So no, I don't think optimal experimental design would do anything more clever in this case. This is not about extrapolation error control. This is about blowing up the error by kind of not making progress, because this weighting is just not really sensitive to what the policy is going to do overall. Yeah, it's very clever. So I'm not going to explain the details of this proof, this chattering. You can read the paper of Dan for the details. So this kind of justifies that if we stick to approximate policy iteration, then we can't expect to get away without this extra blow-up factor. But who said that we need to stick to approximate policy iteration, right? And so what Dan is arguing in this paper is that maybe we should switch to policy gradient or do something like that. And he shows a result which shows that policy iteration does have a chance. It's like, it's a result that that shows that, okay, if we can implement and pull out this policy iteration, sorry, policy gradient, it's optimizing what? Like what should it be optimizing? Well, it should be optimizing this metric, that like the average cost that we care about, right? So it should be maximizing this, and then you take gradients with respect to this. With respect to some parameterization of the policy, and in this case, he chooses the policy class, its state aggregation, to be the ones which are constant per cluster, right? Like you have one distribution over reactions per aggregated states. It makes a lot of sense. And then the result shows that if you take any stationary point, so this is this metric. Any stationary point of J that you want to maximize, then the same thing, but no an upper bound. This is going to be upper bounded by 2 times, I guess maybe for me it's the 4 times, because I'm defining the approximation error slightly differently, over 1 minus gamma. So instead of a 1 over 1 minus gamma squared, you only have a 1 over 1 minus gamma. And as I said, this has the scale of 1 over 1 minus gamma. So some people, in fact, normalize the value functions, pre-multiplying everything with 1 minus gamma, so that they are in between 0 and 1. If you do that, then this looks much better, because then you say that, okay, the 1 minus gamma Wow, this is equivalent to saying that 1 minus gamma times this is 4 less than this, right? And then you just call this V tilde star rho. So this is just like these guys together, and then these guys together. That's the normalized value for pi with respect to the initial distribution. And that's just like 4 times the approximation error. So if you can efficiently converge to the stationary point of this objective function, then you just removed this extra blow up of 1 over minus gamma. And well, it's not reasonable to expect that you can do better than this. I mean, like, it's up to constant factor.
Right. So Chaba, here is J pi the policy gradient, like one step. What is that operator?
J pi is not an operator. It's just a definition. Like, so I'm just renaming this object, the V pi of rho. It's like the average performance of policy pi when it is studied from rho in the discounted setting.
And then what does it mean to say that pi infinity is a stationary point of J pi?
So that means that there is no direction you could move from pi and remain in this restricted space such that you would be able to improve the value of J. So you might be at boundary, but like, you know, like the usual, like you're here and the improvement directions must be orthogonal to the boundary of the space. So this is your policy space, pi. So if you want to increase J, you would need to leave the space. You are not allowed to. You're at the maximum. So this is the result. Oh, by the way, so here the definition that then uses is for all those policies, it's a slight variation of what we have. These are the policies which are compatible with the feature. So what do we mean by that? Well, the policies can depend on the state action pair through the feature map. So any function of the feature map is allowed, but you can't see the state. You can only see its feature. Okay? And for state aggregation, these are just like the piecewise constant policies. This is super simple. And since the supremum is restricted, of course, this is slightly smaller than the usual definition. So I should put a tilde on it. So there is a little gap there. But I guess because we didn't have this restriction when we defined this approximation error. And no, this is a lower value. So we wish to have a lower bound that uses the higher value, but yeah, maybe it works because in state aggregation, everything works. So I didn't check it yet. Okay. So this is one possibility for sure. But today I wanted to talk about another possibility because this goes a little bit too much outside of the things that we sort of up to today talked about. I will come back and talk more about policy gradient methods and policy search in general. This idea that you should search directly in the space of policies, and can you do it? Can you do it computationally efficiently? When can you do it? There are interesting things to say about this. But it turns out that, well, there is, well, I don't know how to say it, but like I stumbled upon a method in my past where you can also reduce this dependence of the approximation error by this 1 over 1 minus gamma factor. And this is a very elegant method too. We call it Polytech, and a lot of people have, or some of the people here might have heard about it. What is this acronym? It's policy iteration with expert advice. So Polytech, yeah, there we go. And yeah, the method has a long history. Kind of stole the idea from a paper. Just today, you might have seen, if you came to the RL theory seminar, a talk that was presented about MDPs and learning in MDPs with changing costs or changing rewards, adversarially chosen ones. And in this context, what I'm talking about is a very natural algorithm, but then you can import it back to the standard setting, and then we see that the idea that was worked out for this adversarial setting happens to be not a bad idea, because it can improve this dependence on the approximation error. And I find that quite interesting. Okay, so how does this work? So this algorithm is going to produce a sequence of policies, like in policy iteration. But it's going to do it in a slightly different way. So you start with some policy, you get a second policy, and so on and so forth. And you have the nth policy. And whenever it has a policy, then we approximately evaluate that policy. So think about that. This is like close to the action value function of that policy. And then instead of greedifying with respect to that, that's the step that is going to be different. We're not doing that. We are doing slightly different things. We are softening this up. But it's not just like with respect to the last action value function, but it's going to be with respect to the sum of the action value functions that we have seen. So it's like this operation is going to be an interesting one. Okay, let's leave this. Okay, let's just color it differently. And so this is like the interesting step. And then you do a policy evaluation, and so on and so forth, and then you repeat. You get your next policy, and then okay, that's the interesting step. And then you get this, and so on and so forth. So what are these red arrows? How does it work? Everyone have heard about softmax or the Boltzmann distribution. So this is going to be Boltzmann. So pi of k at A given S, so the probability under this case policy of an action given S is going to be proportional to e to the power of some eta which is going to be a tuning parameter, times the sum from 1 to k minus 1 of the approximate value functions. Okay. So if you call this guy, I don't know, E K S A, it's like an unnormalized probability distribution. Then the pi k of AS is simply just this EK SA divided by the sum of EK SA prime over all A prime, all of the actions. Okay. And eta is going to be a tuning parameter. And in this step, in the policy evaluation step, we just use this least squares policy evaluation that we used in our API routine with the G-optimal design. And rollouts of lengths H and M rollouts. And then just solve the least squares problem. And that's how you get your action value function. So it suffers from the same problem as approximate policy iteration, that it needs the G-optimal design. But let's push that aside for now, because I just want to argue that by doing this simple change, instead of gridifying with respect to the last action value function, just sum up all the previous action value functions, and then create this probability distribution by considering the Boltzmann with respect to that. We can reduce the dependence of the approximation error from the invariant, like quadratic scaling with the effective horizon, to the linear scaling with the effective horizon. Okay. Is there any intuition, you may ask? Maybe. I mean, there is a lot of good reasons of why this should work. But maybe a very high level of intuition is that if there are some random errors here, then by summing up these guys, you kind of like slowing the process a little bit. You're kind of like stabilizing the algorithm, right? So maybe the big thing to say is that this is just a stable algorithm compared to policy iteration. It's not going to change the policies as crazily as policy iteration can change the policies. And stability in general is good. So I don't know whether you can call this an intuition. It's more like a rule of thumb that if you see some algorithm that can do some crazy unstable things that usually not that great, if you can stabilize it in some reasonable way while keeping its attractive properties, then you'll do well. Are there other ways of normalizing these action value functions, whatnot? Yeah, well, probably yes. If you see the theory, you will understand that yes, there are. There are probably many ways of doing this, not just the Boltzmann distribution, but the Boltzmann is kind of convenient. What about computational cost? Did we increase it? Not really. Notice that we are super lucky. These action value functions are linear, right? In the parameters and the features, right? So this sum, like you might think that, oh my gosh, like I have to perform this sum every time. No. Yeah, you don't have to do that. you just recall that all this amounts to like estimating these action value functions. Okay, I think red is should be reserved for the really important thing, like which is this. So this is blue.
Chaba?
Yeah.
I was going to ask, does averaging out the sum of the Q values, will that help with the initialization issue of softmax or not really?
Then what's the initialization issue of softmax?
You know, like imagine you initialize your Q function to be like put way too much weight on the suboptimal action.
It doesn't, for this algorithm, it doesn't matter how you initialize.
Okay.
You actually initialize pi1, right? In some way.
Okay, so you initialize pi1 to be something.
And then you try to avoid. See, pi1 is an arbitrary policy. It's like maybe it's a bad policy. Of course, you should try hard not to choose a bad policy, but if you happen to choose a bad policy, it doesn't hurt you too much.
Okay.
Right. So okay. So recall that Q of k is just like this phi theta of k. So the sum of Q of j is just the sum of this thetas. This is a Q, right? We can just move the sum there. So all in all, what this means is that, well, you should sum up the parameter vectors, okay? And when it comes to this doing this calculation, okay, let's say the sum of the parameter vectors. So theta, I don't know, bar. Well, that's a bad notation, but anyways, of I don't know, k minus 1 is just the sum of these guys. All right. So then when it comes to evaluating this sum, then you can just take this parameter vector and then multiply it with the features. Super simple. So it's basically you have two loops. You have to calculate the theta, the most recent theta, and then you add it to the sum of the previous thetas. Okay, that's not two loops. It's just like, it seems like, okay, there are two loops, but like you can do it incrementally. And that's it. Okay, so that's Polytech. So why does it work? So let's introduce, so there is an initial state that we are doing all our planning for. That's our initial state. And what we want to claim is that you run, like you have an initial state, you run Polytech, and it's going to be sensitive to this initial state. It comes up with, okay, like it comes up with this sequence of policies. What do you do with it? Well, you kind of take their average. So what's the average of these policies? Well, by that we mean that you simply choose uniformly at random an index between 1 and n. And the action that you're going to choose is going to be the action that is recommended by the policy with index k, this randomly chosen policy at this state S0. Okay, so that's what the planner does. Okay, so this is Polytech planner. And at every initial state you do this, at every state you encounter. And then so Polytech is a local planner. It induces a policy. Okay, So let's call the resulting policy pi. So what can we say about the value of this policy? Okay, so the value of this policy, of course, let's care about some state S. Well, the value is defined as the expected value under the policy, starting the policy from that state of the return. So return is just the usual trail. And now, notice that if I fix an initial state and I take the distribution induced by this policy, it's very close to one of the homework exercises. This is just a mixture of the distributions that you get under the K policies that you get from 22 localize and yeah. No, okay, so Polytech doesn't need to do the init, like, okay, so Polytech is going to be global planning like API. So I take it back. Like you don't need to localize anything. It's just like API, you know, like global design, you just run it, it estimates action value function parameters, it estimates this policy. All right. And because the policy in like the distribution under this induced policy is just a mixture of the distributions under the individual induced policies. This expectation is just the average of the returns under these policies, which is just the average of the values of these policies in this state. So if you want to prove that Polytech induces a policy with a high value, it is sufficient to prove that the average value of the policies induced is high. So high compared to what? Well, let's say high compared to, I don't know, the optimal value function. So there is this policy, pi star, which is optimal. And let's compare the values that we get. And we want an upper bound. So this is optimality gap, right? Like V pi star, that's the optimal value at state S. It's higher than the value of pi k. Sum up all of these. And then we are looking at this. These are value differences, right? So what do, like, if we see value differences, what's the reaction? Like what to do? Like you see differences of values of policies. What jumps to mind? I hope something jumps to mind. There is an identity for this, right? That's been very helpful to analyze policy iteration. It's called the Value difference, yeah, I just call it identity, not lemma. Wesley, thank you. So the value difference identity, all right. So how does it look like? It just says that, okay, take this. This is equal to, this is one thing that is worthwhile to remember, right? So let's scratch this as, because, okay, like later on, we can put back the s if you want. So if we have this sum, we have the value difference identity. So I can pull this out, and there are all these differences that remain. Okay. And we deal with action value functions, not value functions. The value functions are there because we need to care about state values, but the algorithm actually uses action values. So the action value function of, so t pi star applied to v of pi k, what is that? That is just the reward on the pi star plus gamma times p pi star and v of pi k. And that can be written as, the sum with respect to, all right, no, okay. So we had this very well worked out notation that if you have a policy that it induces this this operator that takes action value functions, and then it plugs into the action component what the policy suggests, right? So this m pi of q, so q is an action value function. This maps into value functions, state functions, and this is just equal to, well, if the policy is stochastic, that's the general case, stochastic memoryless policy, and this was just this. Okay, right. Then recall that r of pi is just m of pi applied to r, where r is viewed as a two-argument function of the states and actions. And p of pi is also m of pi applied to p, where p is this transition operator. So in both cases, you have m pi appearing. So here we have r pi star. So we can pull everything out, and then we get r plus gamma p and v of pi of k. All right, so what's that? That's our friend, q of pi of k. So that's the action value function of this policy pi of k, right? And also it's true that v of pi of k is equal to this operator applied to q of pi of k. So using these two guys, we can continue rewriting everything in terms of action value functions. So now we have m pi star q of pi k minus m pi k q of pi k. And this is where I'm going to stop, because now I will need to explain something bigger about this softmax. Like, where is this softmax business coming from? So the next steps are going to be, we don't have this, but we have this q of head of k, so let's just replace it and then subtract and then argue that if you do that, could I just do this very quickly? Times, and here we have these error terms. So we decompose the error into two terms, term 1 and term 2. Term 2 is controlled because we are fitting q head of k to fit well to q of pi k. So that's the job of the features, the least squares policy evaluation, the optimal design. And we already had the result that was saying that these errors are going to be controlled and how big they are. Okay, so we know that for every n, like every k, the error is going to be something like approximation error times square root d plus a bunch of other terms that you can control by making the trajectories longer and then sampling more. But the only blow up is the square root of d. And of course, from this operator, this I minus gamma pi inverse, you get a 1 over 1 minus gamma. So from this, you will see that, okay, the approximation error is going to be divided by 1 minus gamma is multiplied with square root d, but like there is no 1 over 1 minus gamma squared anywhere. And so if we manage to control the first term, then we'll be golden. All right, so that's the idea. Right, so we argue that to guarantee a big value, we need to control the average. For this, we need to control, well, okay, you can divide everything here by n if you want, right? So then you see that here the errors, like they just come up and like they just scale. They don't scale with n, right? Like you can make n as big as you wish. They don't grow. And so what remains to be done is to show that the first term can be controlled. And apparently the idea of this whole Polytech algorithm is coming from first writing this error decomposition, writing all of this, and then starting at this and then saying, well, how do we control this? And it turns out that there are like known, like this is a known problem. This was like, you can, like you started it, and if you know a little bit of the machine learning literature, you realize that, well, this has been studied in some other part of machine learning. It's called online learning, and we know very well how to control error terms like this. And that's where this softmax business is coming from. Like it's a deliberate choice. It's not just like we made it up and like it's to control the error. It's by design, by choice. Okay, so I stop here, but I'm happy to take a look at the chat and answer questions if, yeah. All right, so there were questions about type coding ages ago. Type coding is this, well, it's overlapping piecewise constant basis functions, mostly binary. I think they are binary, where they're firing. They take the value of 1. Those are said to be the ties, and it is meant to work in Euclidean state spaces of some dimension, I guess, where the ties are coordinate aligned for some reason and chosen randomly in some way. And they're overlapping, and they have a multi-scale nature, and it's like a very interesting choice. And I always encourage everyone to look into the math of that, like why that is a good choice. And there are some old papers which I'm super unhappy about at what depths they're trying to answer this question. They're not really answering my questions, which is whether type coding has any interesting approximation properties, or maybe the extrapolation properties. So now we know that, okay, so we didn't talk about, but in state aggregation, this extra square root of d factor is not there. That peaks in Polytech here. From the least sparse policy evaluation procedure, because this works for anything. But in state aggregation, you don't have to do that. And actually, you can avoid this extra square root d blow up. It's because these feature vectors that belong to different groups are orthogonal to each other for states that belong to different groups. So you kind of have representative states, and like extrapolation is super easy. Like, why would you increase errors? Like, you're not going to increase errors, right? So this square root of d is a worst case upper bound on the blow up of the error due to extrapolation can be larger. Sometimes there's not going to be any blow up, of course. Like, you have one basis function, it's constant. Like, why would any error blow up? Like, nothing blows up, right? So it's just a worst case result is square root d. And in state aggregation, you don't have it. And maybe type coding, it is also either, I don't know, like something is going on, because I don't know, Rich likes it. I think he's pretty careful. And yeah, it would be interesting to look at it. Anyways,
can I ask
what
a
are the
quick
questions? Yeah.
State aggregation, is it pretty easy to compute the core states?
Yeah. Like you choose one representative from each group.
So for tile coding, it would also practice hold.
For type coding, I don't know. That's not the case, because this orthogonality is gone. So in type coding, I don't know. Well, maybe if you choose from each type one, you can prove that that's going to be necessarily and not a bad choice for extrapolation purposes. That would be the first thing to ask, but I don't know the answer to that. You know, in type coding, like there are specific ways of choosing the position, the scale, and whatnot. It's a randomized procedure, and then maybe you want to prove that with high probability this controls the blow-up factor. Like a simple choice would control the blow-up factor. I don't know. Oh yeah, like Banafshar said that state aggregation is type coding with one tiling. Yeah. It's like the tilings, like one way of constructing them is that you have one partitioning, right, of the state space, and then you have another one, which is a different one, and so you have a bunch of these different scales. And you just stack the corresponding feature vectors together, and then that's your feature vector. So Alex, you were asking something about the lower bound and the result of that. Not sure what to make of that. The result of that is just showing, no, it's a very different thing. Like the lower bound result is just showing that API is in a way suffering an extra blow up of the approximation error. Well, we didn't know whether it was extra before we knew that there are other algorithms that can avoid this. But no, I will claim that Polytech, for example, avoids this. Like controlling everything else. Well, okay. It's controlling everything else, but maybe it's not as efficient in a certain way. We will need to talk about that. And maybe there is a real trade-off there. We don't know. And you asked what is the tuning parameter, the eta? I will tell you how to choose it once we got to the end. Like there will be a theorem that says that all is good if eta is chosen in some way, which only depends on quantities that you know. So there will be no sneaky tuning parameter choices. Yeah, Fatima asked, is the policy induced by Polytech the average policy over all iterations by 1 pi n? In a way, yes. It's like you randomly choose one. I guess you could work a little bit harder and then show that even for the last policy that Polytech produces, you get the same guarantees, essentially. As far as I know, no one did this. There are similar results that exist in online learning literature, but this would definitely require some effort to do this. It would be interesting to try to do this because, frankly, this randomized choice bothers me. I don't like it. It's a cheap choice. And also, like now you have to keep k or n vectors. Because what if like you choose the first one? Like, okay, that would be pretty bad.
Actually, just to follow up on that question, is that the same as the definition you wrote down for the policy, which involved the softmax? Like, it doesn't seem like that's a uniform choice over.
Oh no, that's a completely different choice. That was a completely different choice. So these are, yeah, like, yeah, different way of doing things. Like one is doing things in the exponent, and then this is doing things, you know, like outside of the exponent, like averaging after the fact.
Okay, so they're just two different algorithms.
No, they are the same algorithm. They're part of the same algorithm.
Oh, okay.
Polytech at the end needs to choose this random policy. This policy in a random.
Okay.
It produces
so
n policies, and then when it comes to act, it chooses the random action by choosing first randomly one of the n produced policies.
Okay.
And then following that policy. Okay. All right, so we continue from here next time.